Welcome back to ECE 501B. We are approaching exam number 1, which is in 2 weeks. It's 2 weeks from today. It will be the 30th of September. Homework 3 is not due this Monday. It's due next Monday. You have a little more time this time, but you have more assignments for homework number 3. It's dealing with chapter 3 and some additional material. There is review material on D2L, and I hope that's clearly visible. It should be right underneath Unit 2 on the content page of D2L. Today what I want to do is remind us where we were, and that was understanding these two subspace concepts, which is the null space of T and the range of T. And we'll do that via an example. We've already seen this map, this linear map T, but now let's play with it a little bit more and illustrate the connections between the null space of T. And remember, the null space of T is a subspace of the domain. The range of T is a subspace of the codomain. Those are in two different spaces. Until we start working with an operator, they could be different domain and codomain vector spaces. We will look at Theorem 3.4 and actually try to prove it or show where that's coming from. But it now gives us a relationship between these subspaces. It talks about the dimension of the null space of T. Again, that's in a different vector space. And the sum of that with the dimension of the range space actually equals the dimension of the underlying domain space. Then we will look at injective maps, surjective maps, and dimensions, some corollaries, what those maps actually allow us to say when we may have differences in dimension in the domain and codomain. Maybe that immediately tells us something about these particular maps, and we can really infer that information from Theorem 3.4, these dimensional relationships. We probably will only get into the matrix representation of linear maps, but we are hopefully headed towards invertible maps, which then those maps have to be both injective and surjective. And then we'll talk about isomorphic vector spaces, and essentially that means these are similar. If we say these vector spaces are isomorphic, then you can sort of, if you know what's going on in one, it carries over to be similar in the other vector space that is isomorphic. The first part of today, I'm going to be sliding through material just as sort of a refresh or a recap. But we ended last time with this example, and I didn't write down the second part. The first part, I hope, was clear that this derivative map is not surjective when the polynomials are of the same fixed dimension m. Because when you start differentiating a polynomial, you immediately drop it down an order or a power. And so you're not going to fill the entire vector space that is potentially there with an mth order polynomial, m in Michigan. Somebody was asking me yesterday in another class about what's capital N, and I said it's Nevada. And they go, what? Where did that come from? And then we had an A for the A phase, and I said, well, that's Arizona. And Arizona and Nevada, you know, that's a current event. So anyway, yes, well, that's where the current event came from, was the gridiron, which is a grid, so we have to, you know, we have to worry about the grid and whether that grid's smart or not. I don't know what the field on that grid was, whether that field was real or complex. Well, I don't know if it had an imaginary component or not. But, sorry, but we digress. Here are the two different maps, linear maps. The first one, T sub 1, is not surjective, but T sub 2 is. As long as we fix an M, but notice in the second linear map, our codomain vector space is of dimension 1 less than the one we start with. It's of dimension m minus 1. And then you can fill that one up through the derivative map. And in that case, T sub 2 is a surjective map for a fixed m. And that example is trying to illustrate that it is critical what your input and output vector spaces are if you're talking about or discussing a map and whether that map is being surjective or not. Let's now look at, we go from grids to clouds. Now we're in the clouds. We have this surjective map, and this one is trying to show that wherever we start in the domain, we actually can get anywhere, everywhere in the codomain. That's a surjective map. There's not a subset of the codomain that we can get to. We can get to every place. That's what this cloud picture is supposed to be illustrating. That's a surjective map, that the range of T, where we can get to through that linear map, completely fills or touches, however you want to think about it, it gets to every element or every point in the vector space W of our codomain. That's what I'm trying to show by that cloud map. We talked last time about different functions, and I just in passing said, oh, this function, the squared function, is neither injective nor surjective. Question?
So in our example of the W is, we find W as being the dimension B minus 1. Would W then be considered surjective or not? I mean, it's not surjective if they're in the same map. But we're free to be able to pick the dimension W. We can pick the dimension W to be the dimension B minus 1.
Yes, so we are in T sub 2, we are picking W to have a dimension 1 less than the domain dimension.
In that case, is W surjective?
In that case, the map is a surjective map. The domain is m-dimensional. The codomain is m minus 1 dimensional in this polynomial. So, because we picked those. We said, here's our domain. It's polynomial of order m. Here's our codomain. It's polynomial of m Michigan minus 1. And in that selection of domain and codomain, the map, the derivative map or differentiation map, is a surjective map. In the other case, it's not. It's not that the codomain is surjective. It's the map that we're labeling as surjective. The map is surjective or injective, and that's what this next example is supposed to be illustrating, that it's neither injective nor surjective. Injective means we can find a point or 2 points in X that lead to the same result. So I can get to the same output through different starting locations. That's not injective. And surjective means we need to be able, f of x is supposed to cover all values if we're saying that that's the real numbers. And we're not covering the negative half of the real line in this map. And that's what I try to say here. It's not injective and it's not surjective. It's not injective because it fails the horizontal line test, so that f of minus 2 is the same as f of 2, which is 4. And it's not surjective. We never go negative with a squaring function. Is that map linear? No, but it is showing that a map, it's not a linear map, but we're showing a map that's not injective and not surjective. This is a discussion with examples. How's that? Here's another question. Y equal to mod x as a linear map, you would have to, you know what would be required for that to be a linear map. It needs to have the additivity property, and it needs to be what? The homogeneity. If it satisfies those two, then you can show that it's a linear map. Okay. Here, let's look at a linear map, and this is the linear map that we have played with before. Hopefully you now have that captured somewhere, but I'm going to slide beyond the title. But this map is neither injective nor surjective. Let me get all of the different coordinates on there. This is going from R3 to R5. It's going from a three-dimensional domain to a five-dimensional codomain. And now we want to talk about what does that really mean. Now we're mapping a 3-vector into a 5-vector. We maybe can't see this, but you could maybe see something that's mapping the plane into 3-dimensional space, to R2 to R3. Here you have to generalize that concept if we're going from R3 to R5. And this gives the relationship of all 5 coordinates in R5 in terms of all of the coordinates, the 3 coordinates in R3 in the domain. And in this particular map, it would be nice to know, is there some place in R3, a line, maybe it's just the origin, is it a plane that maps to the additive identity in R5, which is what? The 5-vector. It's all zeros. Is there such a line, plane? Is it all of R3? Or is it a point, the origin? And we've already, I think, given that answer in an earlier lecture. And in this case, can we get to all of R5 by starting with any point in R3? Can we fill up R5? Here's where we can get to. We could set all of those 3 coordinates individually or independently to 1 and all the other coordinates to 0. So here's where I found my spanning list for that linear map. And this gives the range of that linear map. And all I did to generate this is I said, oh, let me just take a set of linearly independent vectors in R3. Why don't I just make those the standard vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, and let those see where those get me in R5. And that's pretty easy to do in this linear map. I just set x to 1 and everything else to 0. I set everything to 0 but y, and I set that equal to 1. That gave me my middle vector. And then I finally just say, let me set z to 1 and everything else to 0, and that gives me those 3 columns that I can get to any linear combination of those 3 columns. That's the range of that linear map. And I created that by selecting this set of independent vectors from the domain that live in R3. Now, in fact, those 3 spanning vectors are not linearly independent. there's actually some dependency. I'm not going to show it here, but in fact, the range of T is only spanned by two vectors in R5. So one of those could be shown to be a linear combination of the other two vectors. That's what I'm saying. I could find non-zero coefficients in the reals such that two of those could be added up to produce a third. And these are now two linearly independent vectors in R5, and now you could lay a plane that contains those two lines. So the range space in R5 is just a hyperplane in this five-dimensional, it's a two-dimensional surface in this five-dimensional space. That's as good as we can touch in R5 by selecting any point in R3. We can only get to this two-dimensional hyperplane, which means the dimension of that range space of T is equal to the number of linearly independent vectors in that spanning list. Or we start throwing things out that aren't linearly independent, and we threw out one, and now we have a list of two. We can say that's the dimension of our range space of T. It's a dimension of 2, which obviously is not the same as the dimension of the codomain, which is where we're going. It has 5 coordinates. Theoretically, if we had a linear map that was surjective, it would be filling that entire 5-dimensional space, and we are not. We're only filling a two-dimensional surface in that 5-dimensional space. So now the question was, if I picked a different set from my domain, I think I'm trying to repeat the question because I know they can't hear through this microphone. I hope they can, otherwise it's going to be, so I'll repeat the question. If we picked a different set of 3 vectors in the domain, could we reach other locations in R5? Is that what the question was? And what's the answer? We can maybe get to different locations, but we're still going to be locked on that two-dimensional hyperplane. It's going to be the same space. We picked what? These 3 blue vectors, we can linearly combine those. Those fill up in all of R3, don't they? And we can then theoretically pick any vectors that would be a linear combination of these 3. And those we could say, that's a new V. Let's use that to push through T, our linear map. And in fact, it's not going to give us any new information if we think of where we get to as information. So we're locked for this particular linear map. We are locked on that two-dimensional hyperplane. What we did do, though, which was very important, is we selected 3 linearly independent vectors. You could have picked 3 other vectors. As long as they're linearly independent in R3, you could then get different vectors for your spanning list, but you'll see that those span exactly the same hyperplane that these 2 vectors span. So it's very strong, this result, when we obtained it without too much effort. All we had to do was pick those 3 standard basis vectors, generate these 3 vectors, and then see, are these linearly dependent or not? And if they are, throw it out. So we can go and look at these 3 and we can line them up, and if you're used to Gaussian elimination or some kind of way of identifying dependency on vectors, then you can start tossing these vectors that are linearly dependent on the others. And in this case, those three are not linearly independent. In the codomain, we could only find two, and those two would be found no matter what we started with in the domain. Does that answer your question? So that's a good result, because that means, oh, maybe I just didn't find or start with the right V. That's what you would always be questioning, right? And that would be a frustrating result. If it depended on what you picked, oh, well, my buddy, he got lucky. He picked the right V. So now you just have to be, what? Selective in the fact of I need to have linearly independent, and the easy choice is just pick the standard vectors in, or standard basis vectors in the domain, which is what we did. T is not a surjective map, obviously, because 2 is less than 5. Now we knew why we learned that in elementary school, right? Inequalities. We learned that 2 is not quite as big as 5. And now we're using that high-powered math in college. In graduate school, no less. See? And you always are asking, when is that going to be important? When is it going to be important when 2 is less than 5? Well, when you get your paycheck and you get 5 instead of 2, then it's going to matter. And I bet when you start studying in graduate school in an advanced linear systems theory class, you're going to learn that 2 is less than 5 is important also. Because then you'll learn that that's not a surjective map. Your teacher told you that, didn't she, in 2nd grade? I think that's where I remember learning inequalities. She was drawing fish, and never mind. These fish, now they weren't sardines. They were big. They were big fish. And they were either bigger or less than these numbers. So that was the inequality, was the mouth of the fish. That's how I learned my inequalities. Well, let's get back to this class, and what are we doing? We've already talked about maps, and this one in particular was not injective. And what does that mean? That means it has a non-trivial null space. It has a vector in the domain that's not necessarily just the origin. It's not the 0 vector. Every 0 vector, if it's a linear map, maps to 0. That we learned last time also. But here, what's the null space? It's now spanned by any linear combination of -2, 1, 1. And that is a subspace of R3. It's not all of R3. This is just a line in R3. So the dimension of our null space, I'll finish this and then I'll take your question. This is a one-dimensional line in a three-dimensional domain. And that then says that T, this linear map, is not injective and the null space is non-trivial. If the only thing in the null space was the 0 vector, then we would have an injective map. Question?
Yeah, is this related to the fact that you had throw out one of the vectors?
You guys are just on the ball. The question was, does this have anything to do with what we threw away before? We threw away one vector in our range space, or in our spanning list. So our range space was 2nd order. Our null space, I'm sorry, the dimension of our range space was 2. The dimension of our null space was 1. How big was our dimension of the domain? V. 3. That's important. 3 is equal to 1 plus 2. I knew we would really get some high-level math today. So 1 plus 2 is equal to 3. That's actually where we're headed. That's actually theorem, whatever, 3.4. Let me see if we have a little bit more. Oh, yes, I do have some more. I'm trying to go quick. I want to get there. But here's an example of how this non-injective map, what it looks like in terms of actual, let's say, numerical vectors. There U1, that's obviously in the null space because it is that line minus 2, 1, 1. It's not even a linear combination. We didn't scale it at all. And it maps, like we thought, to the 0 vector in R5. That shouldn't surprise us. We said that U1 was in the null space. Suppose we pick another vector in capital V. I'm just going to pick 1, 0, 0, the standard basis with the first coordinate 1. And that now maps through the linear map. I'm just setting the x's to 1 at y and z are 0, and that gives me minus 1, minus 1, 1, 2, 1. That shouldn't surprise any of us. That's the definition of that linear map and applying it to a vector. Now let's create a new vector, v sub 2. Just is a trivial combination of v1 and u1. No scaling between those, which we could. We could add some scaling if we wanted, but this makes it a little cleaner. v1 was 1, 0, 0. u1 was in the null space of that linear map, and that gives us now a new vector, v sub 2. What if we apply our linear map to v sub 2? Now we are taking minus 1 where x was, we're taking 1 where y was, and we're taking 1 where z was, and that's really what those three terms, where they're coming from in that expression for t of v sub 2. That's just whatever x was scaled by, so it must have been minus x plus y minus 3 in the top row. And we're substituting x, y, and z. That gives us now this vector result, just adding up those coordinates, minus 1, minus 1, 1, 2, 1. That's exactly what v1 produced, the same vector. And v1 is not equal to v2. That's saying via an example. So if you had to come up with, show that this map is not injective, you could come up with this kind of a counterexample. You could find a vector in the null space, just pick any other vector, map it through the linear map, and then add those two domain vectors together and show that they give you the same result through that linear map. Now you cannot distinguish, in R5, you cannot distinguish between starting at V1 or starting at V2. You get to the same point in R5. So you couldn't distinguish between, if somebody said, well, where did you come from? I don't know, I came from A. No, I came from V1. I came from V2. Well, how'd you end up at the same place? Well, I don't know, one of us differs by the null space. See how you could tell jokes or stories? Question. So we will learn, the question is, how do we come up with those vectors? We will, or you will, start learning how to generate these results. You now need to find x, y, and z that would be in the null space, and that now may give you or tell you that you have to have some relationship between x, y, and z, for example. And in this particular case, it just so happens that minus 2x plus y plus z ends up in the null space. The other part of this example was trivial. All I had to do was find a vector that wasn't in the null space and pick it. And the easiest one for me to pick was 1, 0, 0. You could have picked 0, 1, 0. They would both give you a different result, but once you obtain that result for V1, it would be equivalent to the same destination with V1 plus U1. So if you both ended up in town TV1, you don't know if you started in V1 or started in V2. You can't differentiate because V1 and V2 differ by a vector, some linear combination of vectors from the null space. Meaning things in the null space really are sort of hidden from you in that linear map. And that may or may not be important to you in an application. So let's make an observation, and this is getting back, this is where I wanted to go tripsing off before I started showing that we ended up in the same location starting in two different domain locations to illustrate that that map was not injective. Dimension of V, where this is actually the vector space of the domain. In our example, that was the dimension of R3, which is 3. But we've now seen in this example that that equaled the dimension of the null space of T plus the dimension of the range of T. Again, that high-powered math, 1 plus 2, equaling 3. Is that a coincidence? Is that just because of the example that I picked? Here, any answer is correct. You may not know at this point, but that seems kind of coincidental. How did that happen? And it's not a coincidence. It's actually a function, or it's a consequence of linear maps. And in fact, if it's a consequence, it must be a theorem. Here's our theorem for today, one of them. Theorem 3.4 from the second edition. If we are given V, a finite dimensional vector space, and I know that you're going to be tweeting this or texting it. You know, 2 years ago I just had to say you're texting it. Now I have to say you might be tweeting this. So if you're tweeting finite dimensional vector space, you might just want to say, oh, FDVS. And that's what I'll be tweeting now in class. I'll be saying FDVS, finite dimensional vector space. Given V, a finite dimensional vector space, and a linear map, and we have then V is going to be our domain, W will be our codomain. So this is what we're starting with. This is given. Then the range of that linear map T, then range of T is a finite dimensional subspace of the codomain, and the dimension of V, which is the dimension of our domain, is equal to the dimension of the null space of T, where this is actually a subspace of V, or a subspace of our domain, the dimension of the null space of T plus the dimension of the range of T equals the dimension of our domain. And that's a very powerful result. We are going to use it many different times after, of course, we prove it. So let's verify this or try to prove it. But really, and what's interesting is these subspaces, one is a subspace in the domain, the other is a subspace in the range. I'm sorry, in the codomain. But those two dimensionally cannot be any bigger, that they are equal to the dimension of the domain. Let's see if we can show that. Here's our proof. Let's take the dimension of our null space of the linear operator T. Let's say that that's Michigan, M. Now we're going to start using some of these ideas that we've been learning all along. If we know the dimension of that null space, how many vectors is it going to take to form a basis? If we know the dimension is Michigan, it's going to take us Michigan vectors in our basis set. So then there is a basis, let me say that's U1, U sub 2, up to U sub n. And we can find that set of basis vectors that span the null space of T. But that null space of T is not necessarily the complete size of our domain, is it? Think back to our linear map before. Our domain was 3 dimensionally, and our null space was 1. So in that case, Michigan was 1, and the size of the domain was 3. From Theorem 212, we can actually extend this basis to complete the basis of our domain. So from Theorem 212, we can extend this basis. That's just a basis on a subspace, so it's not all of the domain. This basis on the null space of T to a basis of our domain V by adding vectors or as many vectors as are necessary, by adding vectors as necessary. Let's just make those, let's just define something. So let's let U1, U2, U sub m, that's m of our domain basis vectors. Let's complete that with some w's. W1, W sub 2, W sub n. So if that's Nevada, how much is Nevada in our earlier example? What was n, little n? It was 2. So now we would have U1 is just one vector, or Michigan is 1, and Nevada is 2 in our earlier example. That's just to give you something to be concretely thinking about. Let this set be the basis on our domain V. Now, here's a really hard question. What's the dimension of V? Nevada plus Michigan, isn't it? M plus N. So the comment was provided though all those W's are independent, but that is what? A condition of a basis. So our basis has to be linearly independent and they have to span the space. So as a consequence of the phrase or term basis, we know that it's a set of vectors that span the space. These n plus m vectors span all of the domain, and we know that they're all linearly independent. We extended our set of vectors that were linearly independent, that were spanning the subspace of our null space. We had to add Nevada more vectors to complete the basis, the set of basis vectors for our domain. Now, to complete the proof, what do we need? Well, we need to show that the dimension of the range space of T is how big? We assumed that the null space was Michigan, didn't we, in size? The null space is Michigan in size, and we now know that the dimension of our domain is m plus n. M of that is from the null space. Now what do we need to prove? We need to show the dimension of the range space is n, Nevada, in size. We must show that the dimension of the range of T is n. Where the range of T is, in fact, a subspace of W. That's what we want to show. Let's just pick an arbitrary vector in the domain. Let's just pull out a V. If that's the case, how can we rewrite that little v? That was kind of a vague question. I'm pretty good at vague questions. But we can expand any vector v, little v, in the domain as a linear combination of our basis vectors. Everybody okay with that? We can now combine these u's and w's with the appropriate scalars to create v. V then, I'm going to do this in sort of two different pieces. V is equal to a1u1 plus a sub 2 u sub 2 plus a sub m u sub m plus b1 v, no, I was using w's, wasn't I? So I want b1 w1, b2 w2, etc. b sub n w sub n. That's okay. We pick a v, we can rewrite it as a linear combination of our basis vectors, scaled with the appropriate scalars. Some linear combination of basis vectors. Now, what happens if I map v through this linear map T? I want to now replace little v with that right-hand side, and what happens when I hit A1, U1 with t? It's going to be ATU1, and what's TU1? By definition, all of my U's are in the null space of T. Those are all going to map to the origin. All I'm going to be left with then is T, B1 TW1, B2 TW2. Does everybody see that? I now have a B1 TW1 plus a B2 TW2, etc., plus a B sub n T W sub n. And that was because, so if you look at this tonight, maybe you've forgotten where that came from, but hopefully not. Maybe tomorrow you might. I'm going to write it down so we remind ourselves. Since each of those U's were in the null space of that linear map for all L in our set of indices on U up to Michigan. Now, with that, let's see if we can learn a little bit more from what we have. How much effort was put into picking little v? None. We picked that arbitrarily, didn't we? Notice that since v was arbitrary, then we can really sort of make two observations. One, what do we know about TV? Besides, there's not much to watch on Wednesday night, not at 5 anyway. I'm sorry, where were we? TV. What can we say about TV? If V was arbitrary, what's TV give us? Pardon? It gives us something in W, and it's going to give us, it's basically going to be the range of the linear map, isn't it? Since V was arbitrary, we can now pick that. It could have been picked anywhere, so that's going to give us the ability to map or span the entire range of that linear map. Is that okay? So TV will span the range of that linear map T, which I'm calling R of T, and I said it would give us a couple of things, or we could make a couple of observations. No matter what we picked for little v, TV now can be expressed as a linear combination of the basis, or of these w's. So any TV can be expressed as a linear combination of these W sub j's. Or stating that second point another way, thus, the list of vectors TW1, TW2, up to TW Nevada, that list of vectors spans the range of T. So now I do mean W's, because now what I'm saying here is TV. TV gives me a vector in W, capital W, and now I can span or write any vector in the codomain as a linear combination of these TWs. Now I'm saying these TW1, TW2 are vectors in capital W, and the B's are scalars, linear combinations. I'm going to write that then as a box. I'm going to say the range of T is now in the span of T WJs. Now, what are we trying to do? We are trying to find a set of basis vectors for the range of T. We've now found a spanning list, haven't we? What do we need to do now? What's the basis? Now I have to show that those vectors not only span the space, they are linearly independent. I can start throwing away things that aren't linearly independent because I really want a linearly independent set of vectors. Then I can count those up and I can find the dimension of that basis set if I have any redundancy in that set of spanning vectors. To complete the proof, we need to show that this spanning list is linearly independent, and that we're not going to throw any of them away. To do that, let's look at the following. Now consider a linear combination of these TW sub J's. And it's going to be a special linear combination. It's going to be such that C1 TW1 plus C sub 2 TW sub 2, etc., plus C sub n TW sub n is equal to 0. So let's form this linear combination of C's with these TWs. Let's say we can find those C's. We've got a set of vectors. I can linearly combine these vectors to give me the 0 vector. That's all I'm saying, with a particular choice of scalars, C's. But what do we know about the linearity of that map? Or maybe what I should ask is, can we use one of the properties of a linear map to maybe rewrite this expression? Can we slide those scalars through that linear map and have T operating on C1, W1 because of homogeneity, right? So now from homogeneity, the above equation in fact equals T operating on CW1 plus C sub 2 W2 plus C sub n W sub n, and that is equal to 0. Ooh. What's that say about that argument. This is saying that that vector in the argument of that linear map maps that vector to the origin in W. What does that say about that vector that I've highlighted in red? Where does that live? It has to be in the null space of that linear map. So now, thus, C1W1 plus C sub 2 W2 plus C sub n W sub n is in the null space of T. Oh boy, this is kind of fun. So, if we have a vector that's in the null space of T and we have a set of basis vectors for the null space of T, what do we know about that vector? We can write it in terms of those basis vectors, can't we? That are the basis vectors of our null space. So, we can expand this vector, where this vector is this guy. We can expand this vector in terms of these u sub l's, since that vector, or it, lies in the null space of T. Well, let's just write that down as a formula. We know that the vector C1W1 plus C sub 2 W sub 2 plus C sub n W sub n. We know that we can make that be a linear combination of the basis vectors. So let's just say that's D1 U1 plus D sub 2 U sub 2 plus D sub m U sub n. Now, what do we know about the u's and the w's? They are independent of each other, aren't they? They're linearly independent because we pick those to be a basis of our domain. So now if I have a linear combination of vectors that are, how do I want to say this? How can I combine can I combine a set of linearly independent vectors to equal some other linear combination of those vectors? I can, but really not, can I? Because my coefficients have to be 0. If they're linearly independent, so if somebody said, yeah, you can combine them, use 0 for your coefficient. But that's basically, no, you can't linearly, or you cannot combine these linearly independent vectors to equal some other linear combination of those vectors. But that's just what we said here. We said some vector is a linear combination of the u's. Well, that's forcing a result, because you just, by scrolling up, we have reached a big but. But these vectors, u1, u sub 2, u sub m, w1, w sub 2, w sub n, are linearly independent by the way that they were built or by construction, by design. They were linearly independent. What does that mean then about the C's and the D's? All those scalars have to be 0 for this equation to be true, because none of these linearly independent vectors can be equal to any other linear combination of those linearly independent vectors. Or you could put them all on the other side, or the D's on the other side, the DU's, that's equal to 0, and then what do you know about all those coefficients? Those linearly independent vectors equal to 0, the only way that happens is for those coefficients to be 0. Another way of thinking of it. Thus, C sub i's and D sub j's are equal to 0. I have a lot of transitions here, but if the C sub j's or the C sub i's are all 0, if the C sub i's equals 0, remember we had an equation up here. Now I'm looking at this equation. If by construction all of those C's have to be 0 in order to end up with 0, what does that say about the TW1, the TW2, the TWN? They are linearly independent. They were spanning, or they were vectors in our spanning list. Now we've just shown that they're all linearly independent, because the only way for this to be true is for those C's to be 0. Let me try to write this down. So this is now, if the C's sub zeros or the C sub i's are all 0, then C1 T W1 plus C sub 2 T W sub 2, etc., up to C sub n T W sub n, that being equal to 0, this relationship implies that all of these TW sub j's are in fact linearly independent. Yes? Well, what we did is, so the argument is kind of, when did we find these C's to be 0? I'm kind of saying we found these C's to be 0 based on this equation, and now we can go back and we can say that's independent really of what TW1 and TW2 were. TW1, TW2, and TWN were spanning vectors in this list. Then we came up with, we said, let's just find this collection that equals 0. The only way that we could have found this equation to equal 0 is if the C's are equal to 0. If TW1 and TW2 were actually the same vector, I could have picked C1 to be 1 and C2 to be minus 1, and that could have been 0 here. But in fact, that's not going to be true because this relationship. This relationship said by construction, all of our U's and W's were linearly independent. So now, what does that say? Now, all of these TW's these TWJs are linearly independent and they in fact span the range of T. That's the definition of a set of basis vectors. So these TWJs are in fact a basis of the range of T. Yes? So this list by construction was linearly independent. So there's nothing in there that's dependent. We can't throw any of these vectors away.
This means after cancel one or two vector image, the remains list are also linear.
Well, you could throw these out, one of these out, and the remaining list would be linearly independent. Yes, but we need this to be a spanning. We wanted this to span all of our domain. Yes, W1 through Wn are linearly independent. Yes, so all of the C's and the D's have to be 0 because of that. So now this list of vectors, TWJs, are a basis of the range of T. It's not so much that we have that. What are we interested in? We're interested in how many vectors are in that list. We need the dimension of the range of T. With this information, then, the list of TWJs is of length n. So the dimension of the range of T is equal to n. And that's what we were setting out to prove, if you can remember back what we started with. Therefore, the dimension of our domain, which was n plus m, is equal to the dimension of the range of T. Well, maybe now I've forgotten which was which, but it tells me right above. That's n plus the dimension of the null space of T, which was n. Okay? And that is very important in terms of some results that follow from this theorem, and those results usually are, if they follow from a theorem, are usually called corollaries. So some interesting corollaries follow. Corollary 3.5. No linear map and again, remember, we're tweeting, so no linear map from an FDVS, finite dimensional vector space, to a smaller finite dimensional vector space. So let's say we have a linear map that maps R5 to R3. That's what I'm saying here. no linear map from a finite dimensional vector space to a smaller finite dimensional vector space in terms of dimension can be injective. That's our corollary. So if you have a R5 collapsing down to an R3, you're guaranteed that that's not an injective map from this corollary. A way to think of that is we have fewer vectors in the output space, and as a result, some input vectors some of those input vectors must produce the same output. This is just screaming to go to the cloud, isn't it? So here is our V, and here is our W. And what we're saying is that well, maybe I should have. Let me try to draw that to the same point. We have then here dimension of V, whoops, is big, and the dimension of W is small. Where now we're mapping this with this linear map T, the proof actually can rely on that theorem, but really what this is saying is when we go from a big vector space to a small vector space, we actually have a non-empty null space. And you've seen what happens with a non-empty null space. We can pick many different vectors in the domain and end up at the same location in our codomain. Let me quickly write down the next corollary, which is just sort of the opposite relationship. It's about surjective maps, corollary 3.6. No linear map from a finite dimensional vector space to a bigger finite dimensional vector space, again, where bigger is in terms of dimension, can be surjective. By that, now we're starting with a small V and going into a big W through this map T. So the dimension of V is small, and the dimension of W is big. And the other sort of way of thinking of this is that fewer vectors in the input space and for that reason we can't produce all vectors in the output space. We just don't have enough flexibility. Or this is saying the range of T does not span W, where this is the, whoops, W is our codomain. And we'll pick up after this, which is now trying to think about these linear maps in terms of matrix representation. So far, we've just been talking about generic linear maps. Now we'll start looking at these as matrices, these linear maps. We'll start there on Monday.